Hello, welcome to the Jungle Gym workshop. In this tutorial we're going to take a look at the framework structure for the framework bare bones, how to use it, how to add to it, and how to get your project up off the ground. This tutorial will assume that you have loaded MPLabX. At the time we made this video, version 6.2 is the latest. It also assumes you have loaded XC32, that you have run MPLabX and installed the recommended plugins, that you have Snap module or one of the other debuggers, the cable that connects the debugger to the Nitro module, a Nitro module, and the associated USB cables appropriate for this application. So we begin with by going to the framework directory, copying the bare bones framework. Now we are going to go back to the My Projects directory and paste that framework here. It is important that you do not edit the frameworks in the framework directory, because if you do something that messes up the configuration, you will not get any of your projects based on that frameworks to work correctly and will have to download it again. This way you keep the copy of the frameworks in the framework directories, and it's only ever referenced, never used. So what we're going to do here is we're going to rename the framework. We're going to call it Lesson 1 Flash LED. Because in this example we are going to load the framework and flash the LED. Okay, now we are ready to launch MPLabX. Okay, what I'm going to do is just to close the start page here, so our workbench, our workspace is free and clear. We will open a project, Nitro, My Projects, Lesson 1. The project is named Frameworks Barebones.x. That is the directory that all the project files are located in. Now what we are going to do is we're going to select Frameworks Bare Bones from the Project tab. Go down to Projects, rename, and we're going to call it here Lesson 1 Flash LED also, and you need to click this box to rename the project folder. Okay, now let's take a look at see what has been loaded and where things are. Alright, in the source files we see there's app.c. We'll go over what that is in a little bit. There's a directory called config. This contains all the items that Harmony has installed that do the project initialization and the CPU initialization. There is main.c, which is the main body of the program, and then there's a folder called Nitro, and inside Nitro is a HAL.c. HAL stands for Hardware Abstraction Layer. What this does is this takes the names that are make more sense and equates them to maybe the peripheral names, which are a little convoluted. So what we're going to do first thing is we're going to change the name of app1c. Now you just don't do that, and you need to do this right up front before you've made any edits. So we're going to load MCC. And this has been taking a little while on this machine. The cache, sometimes you need to go in and on MPLABX and delete it because it gets to be so large it takes a while to find some of these items. MCC stands for Microchip Code Configurator, which configures the system. Alright, here you see a few things. There's a device family pack, which is the things that the compiler loads to support the particular CPU. There's a system. If you click on these items, it brings up all the settings in there, and these include the startup fuse settings and a lot of other information. This is Harmony's core. That's what we're going to look into right now. So select Harmony core, then in the configuration options, open generate Harmony application files. We're going to open that up. Application configuration. You see there's one application that's been configured. We're going to open that up, and here you see the application name. So we're going to change this to Flash. They will also, it has to be a valid C identifier, the name, and should be short and lowercase. So we're going to follow that convention. We're going to call it Flash. Now we have changed the name, but we have not built it back into the project. So over in the project resources, which is where items are, shows the items that are installed in the project. Here we have a timer. If you open that up, you'll see it's timer 8. There's timer 8. We have the core. That's the core. These always must be there and can never be excluded. But there's a button up there called generate. So we're going to click generate. And what it's going to do is go back and generate the code into the project that we just changed. All right, that is finished. You can tell while we say generation complete down at the bottom. We're going to click MCC again to close it. Now we're going to go over to the projects tab, and when we look, we can see that app.c has now been renamed to flash.c. Okay, so here's where we're going to start working on this thing. Let's set up a 1 second flash rate on the LED. That means it needs to turn on and off in half-second periods. So it's off for half a second, on for half a second. So to do that, we don't need to edit anything in main, because what main does is main comes in and goes into an endless loop to cause a system task, which is flash.c. So we don't need to touch main at all. We're going to go into flash.c. Now if we look at flash.c, as you scroll down through it, you'll basically see there's two functions: flash initialize, flash task. May look a little daunting at first, but this follows pretty much the Arduino conception. They have a initialization routine that you put in your sketch, and then they have what they call loop. This uses the name flash task, which is the task we created. You will see why as you add more tasks, loop can't be used, because you'll have multiple definitions of loop. So we're not going to put anything in the initialization right now. Don't really need to. So what we're going to do is we're going to go into loop, and first thing we're going to do is we're going to get rid of this stuff that's in loop to make it look more like an Arduino loop. Okay, so we're gonna add the code in here to flash the LED. Okay, so let's just we're gonna do some bad programming practice. Well, one, and we're gonna put our code inside here. Now what this will do is this will be an endless loop that never exits. Okay, now to know what we're going to do, we're going to load up the hardware abstraction layer header file. And we're going to use the LED user. So it powers up in the off state. So what we're going to do is we're going to toggle the LED user. And you can see right now these are pretty much similar, but at times these names over here, these are the actual hardware calls. And they can be quite different than the English language name, the more sensible name that we give it. So let's copy that. Okay, so we'll paste it here. Whoops, did I copy it? Insert. There we go. So we toggle the LED. Now, it doesn't know when microchip MPLAB-X will underscore things it can't resolve. So LED user comes up as an unknown. It doesn't know what that is. And that is because we haven't included anything into the program or into this file that will tell it what names are. So what we're going to do is we're going to just flip over here and we're going to take the definitions, which is the compiler definitions, and we're going to include also Nitro how. We're going to copy that and we're going to paste that. We'll paste it ahead of the flash call. Okay, so now we have added an include for the compiler definitions for the data types, things like that. We've included how.h. We're done with the main.c, so let's close that. So now when you come down and look, you'll see it goes, now I know where that's at. At the bottom of how are some system level timer functions. And we're going to use delay ms. Okay, and then we're going to go back into Flash. And we're going to delay 500 milliseconds. So what we've done is every 500 milliseconds, because of this delay, we're going to come in and we're going to toggle the LED on and off. So basically it's going to flash at a 1 second rate, which is half a second on, half a second off. Okay, now a word about the compiling. If you just want to build it to see what the errors are, you can click on these buttons up here. These things just build the program. Don't try to talk to the programmer or the compiler. This button with a down arrow will compile the code, download it into the Nitro module. And this button here is the debugger. So we're going to take a gamble. We're going to say this thing's going to work. So I have the Nitro module plugged in. It's powered up. We're going to, and it's going to say, first time it runs, it's going to say, I don't know what tool you're using. If you click the down arrow, here is the snap module. That is what is plugged in. Okay, and now it's going to build the project. It has built successfully. Now it's connecting to the programmer. It has programmed and verified. And now the code is loaded into the Nitro and is running. So let's go over and take a look at the Nitro. Now, as you may remember, I said that this is bad programming practice, what we did here. Now I'm going to try to explain a little bit why, and then the next portion of this lesson we are going to see why it's bad. Harmony is set up to run multiple tasks. The tasks execute one after the other. So let's say we had 3 tasks. What would happen here is the first one would run, which would be flash task. It would come in here and it would never exit, meaning the other 2 tasks or 3 tasks, however many there are, will not ever run. Flash task or loop must do is return, and when it returns, if you go back, remember back in main, it calls system tasks, which executes them one right after the other. It must come back. So what we're going to do is we're going to remove the endless loop here. And now we will come in to flash tasks. We will cause the LED to toggle, and we will cause a delay, and let's download that, and you'll see it's the same result. From looking at the LED, you can't tell which version is running. But this version actually returns every half second. But this is still also bad program practice. Now, why is that? Let's assume we have a second task that is running, and let's assume it is flashing an LED. And let's assume it's flashing it at a fast rate, maybe a quarter second on and off. What will happen here is you will come into this task, you'll toggle the LED, stay there for half a second, return, go into the second task, flash the LED, stay there for a quarter second, return. It then runs this task again, and this task is going to take half a second to return. So what you've done is you're strangling the second task, which wants to run every quarter second. You're forcing it to run only twice a second, not 4 times a second. So that LED will appear to operate in a very similar fashion, and we'll try that and take a look at it. So you may be wondering, how do we get around this? Well, there's tools built into this system that will allow us to get around. And if we look at how, we can see we can load a timer, which does not, the load timer returns immediately. These tasks up here, well, long timer tick is a system only level tick. The ones that return millis and read timer just return values immediately, but is time expired and load timer with MS do what they'll load the timer and then return. So what we're going to do is we're going to load a timer, and you see it's a 64-bit unsigned integer. So we are going to come back over to ours with load timer and MS, and we are going to go up here into initialization. And the first thing we're going to do is we're going to create a UN 64-bit integer, and we're going to call it delay, or DLY, let's say, so it doesn't get confused with anything else. Now what we're going to do is we're going to go down here, we're going to set that timer Y equals load timer with MS 500 milliseconds, just like we did in delay. and we're going to go on. So now what happens is when we come into this loop, we're going to now check to see if that timer has expired. Okay, let's come back over to Flash. If is time expired, and we have to put the name of the timer in here. We have to pass it that DLY that we created. Okay. Now, instead of delaying here, what we need to do, so what happens here first, let's look at this. Well, what we've done is we've loaded the timer at 500 milliseconds. Flash is going to get called by the main body over and over again, and it's going to keep just exiting until the timer has expired. Once the timer has expired, half a second has gone by, it will toggle the LED, and then what we want to do is reload the timer with 500 milliseconds and then return. So it'll wait 500 milliseconds. So effectively, this task is only here long enough most of the time just to check to see if the time expired, which is going to be really fast. So probably 99.9% of the time this program is running, it is not going to be in this task. It is going to be in, it's going to be sharing that time with other tasks. This is called cooperative multitasking. If there's two tasks, and you're giving back any free time back to the system or the other task to use, the tasks are cooperating with each other. So let's build, download, and see what that does. Okay, so now let's try adding another task, and in that task we're gonna flash the LED at a faster rate, and then we'll go back to the original task and see what effect adding those original while loops and things have on it. So we're gonna launch MCC again. Okay, now we're back inside MCC. Let's bring up the core. We're gonna look at the application files, and we're gonna go over here to the number of applications, and we're gonna increase it by one more. That's 2 applications. Then we're gonna look at what the name of that application is. Here it is called App 1, just like the original one was called App. We're going to change it to, let's call it Fast Flash. Okay, and we're going to go back over here to the Resource tab, and we're going to generate the program. Generation is complete. Exit MCC. We'll go back to the projects, and now we see it has added Fast Flash. Alright, so now we're going to take a look at Fast Flash. Now let's go back and look at what Fast Flash has as its default program here. So there is an initialization that we had talked about, and a task function. Inside the task function is a state machine, and the first case in that state machine is an initialization. So this initialization occurs early in program startup. We can go over and see where that occurs. In main, when sysinitialize is called, that's where that first initialization. The second initialization occurs in systask, the first time it runs each task. So we go back over here and we can see that they basically set this app initialize to true. If it is true, then they set the state machine to point to this state. So what we're going to do is we're going to go and copy this. And what we will also do at this point is change this to a static, which means it can only be seen locally inside that one file. We'll go over to fast flash and we will add the same statement. And we are going to come up here because it doesn't know what DLY is, and we'll add it here too. Okay, so what we have done is, in this second chance initialization, I call it, we have added that delay timer, and then it's going to come down and run this task. If we go back to Flash, we can copy the same code from here, bring it into Fast Flash, and add it here. Okay, so now this effectively is the same as the flash.c. Again, it's telling us it does not know how to resolve that issue there. So we will copy the same include files over to Fast Flash. Okay, now we have basically the same thing, but we're going to flash a different LED for this LED. We're going to use the one that is connected to the RX. That's called LED 3. So we will put this in here. So now what we have done is we've started a timer, and we're going to flash it at a much faster rate. Let's go to 200, which is a lot quicker. Okay, so it's going to come in here, it's going to initialize the timer, it's going to then set the case to the service task case, and then from then on it's going to just continually come in, services case. It's going to look for the expired time, and it should be ready to go. So okay, so now let's just go ahead. We're just going to go for bear. This is pretty simple. Let's just run it and see what happens. We will use a debugger at some point in time. That's a feature you guys are probably going to want to see. Okay, so now if we look, we can see the bottom LED is flashing at the 1 Hz rate, and the one above it is flashing maybe twice as fast or more. So now if we go back and we look at Flash, and remember how I said if we, let's just comment out this stuff for now. So we have LED user toggle, and now what we are going to call is we are going to go over here and we're going to call the delay MS, as we had talked about. And we're going to just delay at 500. So this again is going to flash this task at the 500 millisecond rate. Let's just go ahead and compile. Now if you look at what happens, both LEDs are flashing at the same rate. We did not change how fast flash operates, but both LEDs are now flashing at the same rate, and that is because this delay here, which is causing flash task not to cooperate anymore, is basically setting the pace for everything. So even though that other one is delaying a shorter period of time, it still is only being serviced at a 500 millisecond rate, because for 500 milliseconds it sits here both when the LED is on and then another 500 milliseconds when the LED is off. So it's getting very little chance to operate. The other thing you will notice is, like I had said in the beginning, is if you do this, what is going to happen is it's going to tie up the entire system. Let's download that and you will see that. This way the only LED that should flash would be the bottom LED. And as you can see, only the bottom LED is flashing. The reason is flash task is executing, never ending. Fast flash is not having a chance to operate. And again, this is called cooperative multitasking. And when you do this, you are not cooperating. What would be cooperating would be to put this back the way we had it. I forgot to take out the delay 500. Now let's try that again. Okay, there we go. And you can see the fast flash is occurring at a rhythmic rate, and so is the slow flash. All right, so let's look at the using the debugger. So in the source file, you decide where you want it to halt. Let's say we want it to halt at this load timer function. We come over to the line number, we click on it, puts a red box there, and of course highlights the text line in red. Now we come up to the top, we debug the project. That'll recompile the code if it needs it, and it'll run the program and stop. Now occasionally the debugger will stop at the line before, and that has to do with program optimizations. If you turn off all optimizations, a lot of times it fixes this error where it stops on the line before the line you really want. If we step over, now we're at the breakpoint line. Step again. Now it's going to check to see if it's initialized, and it's going to return. And this goes into the systasks, and that causes it to run back into this application. So what we'll do is we'll now come over here and verify that it does that. And you can see it does. So the debugger in this thing is pretty slick. It does allow you to debug for a $19 debugger. I don't believe the Arduino allows you to debug at all inside their interface. So this is already a leap ahead. Okay, so now let's take a look at one more thing that I get questions on periodically. It has to do with this timer. So if we look at the code where it checks to see if the time expired, it only does one simple test. When you set the timer, it takes the tick, which is the amount of milliseconds the machine has been on. It adds your delay to it in milliseconds and returns that value. So when you check to see if the timer has expired, it takes timer, and if timer is less than tick, in other words, if tick is now greater than timer, it returns that it has expired. Now I get questions about this in regards to what happens at rollover, because this does not take into account a rollover situation. Okay, so what happens here when this timer rolls over? Let's assume the timer is an 8-bit value, so its range is from 0 to 255. And let's say the tick number is right at, let's say, 250. So it's going to go up to 255 and then it's going to roll over. And let's say you added 10 to it. So what that would do is that would set the timer value at tick, which is 250 plus 10, which is 260, which is now a count of 5. Although since it counts 0, it's going to actually be at 4. So what happens is as soon as you set this timer, tick is going to be less than, timer is going to be less than the tick value, which is still at 250. So you set a timer for 30 milliseconds, it's going to expire immediately. The first time you call it, it's going to think it expired because of this rollover. And that could be a problem with systems with time values, especially if you're looking for critical time values. That means that during rollover, you could see a fault. So why is this value set the way it is and doesn't do any other checks for rollover? Well, to understand that, you need to look at the range these timer values and tick values can have. Let's look and see what range this timer has when tick is a 64-bit unsigned integer. So we're going to open up the calculator and we're going to go to x to the y, 64. That's the maximum count tick can hold before it rolls over. Let's divide that by 1,000, which is how many milliseconds are in a second. So this is how many seconds. We'll divide that by 60. This is how many minutes. Divide that by 60. This is how many hours. Divide that by 24. This is how many days. And we'll divide that by 365. Okay, so now this is how many years before that time rolls over. And you can see it's 584, almost 585 million years. So if you were to have started this timer up when the dinosaurs first appeared on Earth, it still probably would not roll over in your lifetime today. So this counter does not need to bother with checking for rollover because it's just such a big number. Now the reason it's such a big number is right now tick is set for 1,000 counts per second. But suppose you were to change that to 10,000 or 1,000,000 counts per second. That this time here would become smaller and smaller and smaller, and you could get into a situation if this was something like let's say this controller was in something like a refrigerator. It could, when left on in a year or so, have a rollover situation which could cause errors. Okay, so that's pretty much it for the first lesson here. You should know now how to add your application files. You put your code in the application files. Now granted, these were pretty simplistic. We will try to get into some more in-depth ones. You'll see some of them coming up in the RTOS versions and USB version, where we start to add code to actually do other things. So join us on the next video, which is the bare bones RTOS tutorial.